Preparing for an AI Inference Engineer interview? You've reached Interview Guide, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How do you explain the trade-off between inference latency and throughput? Latency is the time one request takes. Throughput is how many requests the system completes per second. I usually start by defining the SLA, because a chatbot, batch embedding job, and fraud detector need different trade-offs. To improve latency, I reduce model size, optimize kernels, warm caches, and avoid queuing. To improve throughput, I use batching, parallelism, and higher device utilization. The mistake is optimizing one metric while silently breaking the other. While answering, focus on defining both metrics, how they conflict, how batching and concurrency affect them, and which optimizations target user-facing latency versus system capacity. Question 2. What is dynamic batching, and how would you tune it in a production inference service? Dynamic batching groups requests that arrive close together and runs them as one tensor operation. On GPUs, this improves utilization because larger batches amortize kernel launch and memory overhead. I would set a maximum batch size and a maximum wait time so tail latency stays within SLA. For LLMs, I would also consider continuous batching, where tokens from different sequences are scheduled together. The key is measuring P95 latency, not just average throughput. Make sure to cover queuing delay, maximum batch size, timeout windows, GPU utilization, tail latency, and why continuous batching is especially important for token-by-token LLM generation. Question 3. How does quantization improve inference performance, and what risks does it introduce? Quantization reduces precision, usually from FP32 to FP16, INT8, or INT4, to cut memory bandwidth and speed up inference. I first try post-training quantization when accuracy tolerance is clear, then quantization-aware training if the model is sensitive. Calibration data must match production inputs, or the activation ranges will be wrong. For GPUs, I prefer hardware-friendly formats like INT8 or FP8. The trade-off is lower cost and latency versus possible accuracy loss and debugging complexity. In your answer, talk about FP16, INT8, INT4, calibration data, post-training versus quantization-aware training, accuracy trade-offs, and hardware support for quantized kernels during real production deployment. Question 4. Walk me through how you would optimize a PyTorch model for deployment using ONNX and TensorRT. An optimized deployment path usually exports the trained model to ONNX, validates numerical parity, then builds a TensorRT engine with chosen precision and shape profiles. I would freeze pre-processing assumptions, test representative input sizes, and compare outputs against the framework model. TensorRT can fuse layers, choose faster kernels, and manage memory better. But engines are hardware-specific, so CI should build and test them per GPU architecture and driver stack. Be sure to mention export formats, operator compatibility, numeric parity checks, TensorRT engine building, precision modes, dynamic shape profiles, and deployment risks across GPU architectures. Question 5. A model service suddenly shows high P99 latency. How would you debug it? When P99 spikes, I separate model compute time from queuing, network, serialization, and pre-processing. I would inspect traces, GPU utilization, batch wait time, memory copies, and cache hit rates. Often the model is not the culprit. A slow tokenizer, cold start, or overloaded host thread pool can dominate. I reproduce with controlled load, then change one variable at a time. Good inference engineers debug the whole serving path, not only CUDA kernels. While answering, focus on separating compute time from queuing, pre-processing, networking, cold starts, memory copies, and thread contention. Mention tracing, profiling, and P95-P99 analysis too. Question 6. What are common GPU memory bottlenecks during inference, and how do you reduce them? GPU memory affects both capacity and speed because inference often moves more bytes than it computes. I reduce footprint with quantization, activation reuse, weight sharing, smaller batch limits, and efficient attention kernels. For LLMs, KV cache is usually the dominant growth term, so sequence length and concurrency matter a lot. I also avoid unnecessary host device copies and pin memory when appropriate. The best optimization is the one confirmed by profiler counters. Make sure to cover weights, activations, KV cache, batch size, sequence length, host device transfers, memory bandwidth, fragmentation, and profiler-driven optimization rather than guessing in production. Question 7. When would you use data parallelism versus model parallelism for inference? Data parallel inference replicates the model on multiple devices and sends different requests to each replica. Model parallel inference splits one model across devices using tensor, pipeline, or expert parallelism. I choose data parallelism when the model fits per GPU because it is simpler and isolates failures. I use model parallelism when weights or KV cache exceed one device. The cost is communication latency and harder scheduling, especially for small batch real-time workloads. In your answer, compare data, tensor, pipeline, and expert parallelism, explaining when the model fits one GPU, communication overhead, failure isolation, and scheduling complexity. Question 8. What is the KV cache in LLM inference, and why is it so important? KV cache stores previous attention keys and values so the model does not recompute them for every generated token. It changes LLM inference from recomputing the whole prefix to appending one step at a time. That improves latency but consumes memory proportional to layers, heads, sequence length, and concurrent requests. In production, I manage it with paging, eviction, sequence limits, and batching policies. Poor KV handling is a common reason LLM servers hit capacity early. Be sure to mention what the KV cache stores, why it speeds autoregressive decoding, how it grows with concurrency and context length, and paging or eviction strategies. Question 9. After optimizing a model, accuracy drops slightly. How do you investigate whether the optimization is safe? I treat optimized inference as a correctness problem before a performance problem. First, I compare outputs against a trusted baseline, using tolerances appropriate for FP16, INT8, or non-deterministic kernels. Then I run task-level metrics on representative data, because small logic differences may or may not affect quality. I check pre-processing parity, calibration coverage, operator substitutions, and dynamic shape paths. If accuracy drops, I bisect optimizations rather than guessing. While answering, focus on baseline comparison, acceptable numeric tolerances, task-level metrics, calibration coverage, pre-processing parity, operator substitutions, non-determinism, and systematic bisecting of optimization changes. Question 10. How would you design a scalable real-time inference service for an image classification model? For an image classification service, I would put an API layer in front of a model server with request validation, pre-processing, batching, inference, post-processing, and metrics. The model server should support warm startup, health checks, versioned models, and graceful rollback. I would keep CPU pre-processing from starving GPU work, and use asynchronous queues where needed. For scale, I would run multiple replicas behind load balancing and auto-scale on latency, queue depth, and accelerator utilization. Make sure to cover API layer, pre-processing, batching, model server, health checks, versioning, rollback, load balancing, auto-scaling signals, and separating CPU work from GPU execution. Question 11. What causes cold start in AI inference systems, and how do you reduce it? Cold start matters because loading weights, compiling engines, allocating memory, and warming kernels can take seconds or minutes. I reduce it by pre-building artifacts, keeping a warm replica pool, lazy loading rarely used models, and running synthetic warm-up requests after deployment. For GPUs, I also account for CUDA context creation and memory fragmentation. If traffic is spiky, I prefer predictive scaling or scheduled warm-up instead of reacting after users feel latency. In your answer, talk about weight loading, engine compilation, CUDA context creation, memory allocation, warm-up requests, warm pools, lazy loading, and predictive scaling for spiky traffic. Question 12. How would you optimize inference on CPUs instead of GPUs? CPU inference is still valuable for small models, edge deployments, and cost-sensitive traffic. I optimize it with vectorized kernels, thread pinning, NUMA awareness, cache-friendly layouts, and libraries like ONNXN or OpenVINO. Batch size must be tuned because too many threads can fight over memory bandwidth. I also watch preprocessing since it often dominates CPU workloads. The principle is the same as GPU serving. Measure bottlenecks before changing architecture. Be sure to mention vectorization, thread pools, NUMA, cache locality, memory bandwidth, ONNXN or OpenVINO, batch tuning, and why CPU inference can still be practical. Question 13. What metrics and logs would you add to monitor an inference platform? An inference service needs observability at request, model, and hardware levels. I track P50, P95, P99 latency, throughput, queue time, batch size, error rate, model version, GPU utilization, memory bandwidth, and OOM events. For ML quality, I log sampled inputs, outputs, confidence distributions, and drift signals with privacy controls. Good dashboards connect symptoms to causes. For example, rising queue time with flat compute time means capacity or scheduling, not model regression. While answering, cover latency percentiles, throughput, queue time, batch size, errors, GPU utilization, memory metrics, model versioning, drift signals, sampled logs, and privacy constraints. Question 14. How do you safely roll out a new model version in production? I roll out model changes like software releases with stronger quality gates. A new version should pass offline metrics, parity tests, load tests, and compatibility checks for inputs and outputs. In production, I use canary or shadow traffic, compare latency, errors, and business metrics, then ramp gradually. Rollback must be fast and automated, because model regressions can look like infrastructure failures. Versioning artifacts, tokenizer, config, and preprocessing code is non-negotiable. Make sure to cover offline validation, shadow traffic, canary releases, gradual ramping, automated rollback, artifact versioning, tokenizer compatibility, and monitoring both technical and business metrics. Question 15. How do you decide whether to run inference at the edge or in the cloud? Edge inference reduces network latency, improves privacy, and works offline, but it faces tight limits on memory, power, thermal budget, and update control. Cloud inference offers larger accelerators, centralized monitoring, and easier rollouts, but adds network cost and data movement. I decide based on SLA, data sensitivity, model size, traffic pattern, and total cost. Often, the best design is hybrid, with small edge models and cloud fallback for hard cases. In your answer, compare latency, privacy, offline operation, accelerator availability, power and thermal limits, rollout complexity, monitoring, total cost, and hybrid fallback architectures clearly for production. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.